Okay, this is a solution summary for problem R, zoo management. This is a graph theory problem in which you're given a zoo with some animal enclosures connected by tunnels, which is essentially an undirected graph. And you're given the animals that live in each enclosure as a set of labels. So for instance, we have types of animals which are given by these numbers here, and we have this red labeling and we have this blue labeling, and we want to find out whether it is possible to move the animals through these tunnels to get from the red to the blue. Now, what can we do to achieve this? The only option we have is we can rotate along any cycle in this graph. So for instance here, in this triangle on the right, we could move clockwise, and then we would transform from this labeling to this labeling. And then similarly here on the left, there is a way to combine along these cycles to go from the red to the blue, and the answer in this case would be yes, or possible, I think. Right, so this is a graph theory problem, but there's also a bit of string theory inside there. So in order to solve this, we first start by eliminating all the bridges in the graph. So because bridges by definition do not have any cycle going through them, we can never use them, so we might as well just ignore them. Which means now we have a graph where every component has every edge belonging to at least one cycle. Now there's one special case, and this is where the string theory comes in, which is if the component is a single cycle, then this essentially becomes a problem where we have two strings and we need to find whether they're cyclically equivalent to each other, which can be solved by any linear time string matching algorithm. So that's the string part done. Now we need to deal with any other kinds of components, and there we need to consider a bunch of cases. First, if there is any edge that belongs to at least two distinct cycles, then this particular means that we have a situation like this here, where we have two vertices and we have at least three cycles that connect these two vertices to each other. And then we can rotate along these cycles. So we first take, say, the right cycle, do a clockwise rotation, do a clockwise on the left cycle, and then do counterclockwise on the two cycles again. And the total effect of this will be swapping these two and swapping these two. Right, and in general what this achieves is any pair of swaps, and if we combine this with the cycles, we can not just swap these specific pairs, but we can swap any pair of pairs. So this means that doing these kinds of operations, we can find a solution for any even permutation, so where an even permutation is one that consists of an even number of swaps. And in particular, if we are in this situation, then we also observe that at least one of the three cycles we can form out of these paths, so either the left or the right or the one going all the way around, needs to be of even length, which means that it is odd as a permutation, which means that we cannot just get all the even permutations, we can in fact get all the permutations. So in this case, we just need to check whether the multi-sets of labels before and after are identical, and then we're done in that case. So once we are done with all that remains is the case where we have these cycles which are only joined together at single vertices. This is a special type of cactus graph. And what do we do in those cases? Well, we can do the same sort of thing. We rotate along the two cycles in one direction, then we rotate back along the other direction, which in this case performs a cyclic swap along these three elements, where again, when we can perform these three cycles, we can combine this with any other cycles to perform any three cycles, which again, by some group theory, means that we get all the even permutations in this graph. Okay, so we get all the even permutations. When can we also get the odd permutations and therefore all permutations? This happens exactly when one of these given cycles is even in length, because again, An even cycle is an odd permutation, and when we can get any odd permutation, we can get all of them by combining it with even permutations. And then you need to combine all this together. It will be a ton of code, but then you hopefully get accepted in the end.